This is a production of Cornell University.
Well, thank you, Louis, for that kind introduction. Pleasure to be here. It took me many decades to get here. I've been wanting to come to Cornell. One time when we were touring the colleges and universities in 2019 for my son, we were scheduled to come to Cornell, and we were stuck in Newark Airport for 36 hours. Okay, so we came close, but not quite. So it's good to be here physically, although I see familiar faces here, and I'm glad I'm on the campus, and good to see you all. Thank you for coming this afternoon here. The room is quite full, so that's nice always. I still see people keep coming into the room. That must be the food, right? And that's a good sign when people are coming in this direction. I have given a lot of talks, and there have been times when people are getting up and going out. And I was in one talk like that. I was sitting up front, and the person who was giving the talk, and people were leaving and leaving and leaving. And then I happened to be the last person sitting up front. So I said, Dwayne, no, the person who was speaking said, Raj, are you really interested in what I had to say? And I said, no, not really. I'm the next speaker. So I'm going to talk about precision agriculture. That has been my bread and butter, my career for the last 30 years. A lot of work has happened with graduate students like Louis Longchamps, who spent 7+ years in my lab, first as grad student, then as a postdoc. And it has been a really interesting journey. So it's a little bit of looking back and then bringing you up to speed where things are today and what we're doing in precision ag in our lab. So let me start with a question. I always like to start with a question. What is this picture? I can give you a hint. Each one of you use it every day. Some people are saying it's a computer and has wheels. It must be a mobile computer then.
I'm not that old.
So this is the first GPS unit that was developed by Rockwell Collins in 1976. Louis mentioned I served 2 terms on NASA board. When I saw this picture first time, it was very intriguing. And in a matter of less than 20 years, it went from a size of this GPS unit, which will fit only maybe half a dozen in this room, to something that you can hold it on the tip of your finger. That's the chip that's in every cell phone. If you have a cell phone that you bought after year 2000, you have that chip, okay? And so it's kind of hard to imagine how agriculture or society or technology will change in the next 20 years, okay? Because that happened. It surprised even scientists at NASA how dramatically we change. You can hold it on the tip of your finger. It's in every cell phone, okay? Now, the initial mobile unit that was given for military purposes, I don't know how many of you have Googled this picture. It looked something like this, okay? And this is me in late 90s mapping nitrogen stress in cornfields in Colorado, okay? So before Kansas State, I was in Colorado State for 20-some years, where I had my entire faculty career. I'm wearing a Velcro tape here with a data logger, which is connected through RS-232 port to Minolta SPAD meter. I have a 2-kilo monochromatic Fujitsu pen tablet with a revolving hard disk, not a solid state. And of course, I'm carrying a bunch of deep cycle batteries to power the Trimble unit. It used to be heavy, and the more you walked, it got heavier, okay? But that's how we were mapping nitrogen stress at that time. And that would be the common theme you will see in my talk today, ability to quantify variability in crop and soil parameters. That's what my entire career has been about. And then creating decisions to make those management, okay? So I now take you to 1983. What happened in 83? Absolutely right. The GPS became accessible for civilian purposes, okay? And so if you took my Precision Ag course, I taught 3 courses at Colorado State. One of the first laboratories we will do is take multiple different GPS units that work on different frequencies, go to a benchmark, and we'll do an error analysis, okay? So you do the northing and the easting, and then you calculate the circular error probable, meaning where does the 50% of the data reside in XY domain? And lo and behold, back then, you're lucky if you're within the 50 meters plus minus 50 meters. And I pulled up paper from IEEE, and lo and behold, the horizontal positioning for standard signal, which is SPS, used to be 100 meters, and what military had without correction, which is precise positioning system, used to be 20 meters. Okay, so we have come a long ways. And if you look at the publications that were coming out during those days, we're focused on, hey, we got access to GPS, and this is how we can improve the signaling and make it more precise and differential. And I don't know if you guys can read the authors here. I want to draw your attention to one individual, Brad Parkinson. Who is he? A lot of people don't know about this. Brad Parkinson is the father of GPS, Global Positioning Systems, okay? A professor in Stanford, and that's where him and his colleagues, 4 of them, they are the brains behind the GPS. In fact, just before COVID, Queen Elizabeth awarded them with a £1 million award for being instrumental in engineering. Okay, all four were done that. And I got to know Dr. Parkinson quite well. I was privileged to be, he's the co-chair, still today, he's the co-chair of NASA board, US Presidential Advisory Board on Positioning, Navigation, and Training. This is one of our meetings in Washington, DC. That's him, and some of you may know Dr. James Schlesinger. He was the first Secretary of Energy, and then he had multiple other assignments. And so I look a little bit younger. I'm still young, right? I want to draw your attention to the person who's sitting right next to me, late Dr. Ronald Hatch. So today, decimeter accuracy in tractor systems or combine systems are so common. He's the brains behind that. So he was the brains behind the Starfire that John Deere inherited, and be able to provide decimeter accuracy without any correctional signals, because they got access to not the encrypted data, but the frequency on dual frequencies on GPS. So, so a lot of contribution there. And while the literature was focused more on, hey, how could we improve accuracy of GPS in those days, there was this individual whose wheels were turning. That, hey, we now have access to, this is late Dr. Pierre Robert, who was designated as the father of precision agriculture, a Belgian scientist, established the first Precision Ag Center in University of Minnesota. Good friend and colleague, he passed away untimely. He was thinking, as a visionary as he was, that how one day location-based agriculture may become a reality. And so after one of these tri-society meetings, ASA, CSSA, and SSA, these colleagues are sitting in a bar in Chicago, you know, with their beer in their hand, and they start scribbling on a piece of napkin here. I reconstructed it, by the way. It's not the real napkin. I don't hold that with me. That one day that we will embracing GPS as a mundane affair. And so IPNI, which is no longer there, International Plant Nutrition Institute, closed down after 75 years, took this to their designers, and this was put together. So this was at one point of time, and Harold may remember this was one of the most widely used infogram for what precision agriculture may become one day. It came out in, I think, in 84 or 85, something like that. But one thing that the founders of Precision Ag cautioned us, that once we are engaged in location-based agriculture, that will give rise to lots and lots and lots of data. And I think that's where we are today. That's exactly where we are today. And so I'll be talking a lot about engagement with data and data analytics as we continue to solve the challenge of spatio-temporal management, looking into the future, okay? Variability happens, right? I was flying in yesterday. I saw tremendous amount of variability in landscape and topography and soil type, crop cover, stuff like that. This is a picture taken from an airplane looking down. It could be anywhere in Colorado, western Kansas, parts of Nebraska, and so forth. And so the fields are not alike. So this is landscape scale variability. I can zoom in on a farm that may have 20, 30 pivots and other rain-fed agriculture, and they still don't look alike. So that's a farm scale variability. I can zoom in on one field where we have done some work, and you still see variability in soil. And that inherent variability is what we have been trying, or my lab, along with several others, were after quantifying without having to actually acquire a lot of soil samples. How could we do it in an economically affordable manner, less labor-intensive manner? And this is where the remote sensing came in, okay? And so it has an implication, because oftentimes, not always, but oftentimes, this inherent variability, I'm going to click next and show you the crops growing on these fields, translates into that crop. Although the entire field is treated uniformly, that inherent variability, if I were to go here, it translates into the crop production system. Okay, so if you're putting 150 pounds of nitrogen across the entire field, you know it's not in your corn, not across the entire field. And that was the whole point. That's the holy grail of precision agriculture. How do we make tailor management systems to feed the entire field? And it has been 30 years since our capability to quantify grain yield, so pixel by pixel. Combine is moving on the motion, we can pick. But unfortunately, even today, how are farmers managing their fields? And so our lab did this quick analysis many years back. So here's your combine. And it's just a schematic here. So it's moving and is harvesting depending on the size of the header, 6 row, 12 row, whatever number of rows. And every second it's dropping a pixel, quantifying how much grain yield is coming from there. You stitch the whole thing together, it becomes a digital yield map. So quantifying how much you're harvesting from each and every part of the field. You go through the cleaning process because there are errors associated with that. Once you have cleaned the data, if you were to run quick statistics, it'll give you the frequency distribution here. And in this particular example, average is 180 bushel to an acre, okay? This example is more than 20 years old. So here's a simple query that you can write in any of the platforms that you're working on. So how many pixels match the average? Say it louder.
About 20%.
Less than 20%? Any other guesses? 0? Okay, is there some pessimist in the room? Yeah, it's a mathematical average, so it doesn't. So in this example, 2%. Okay, and I remember one of my colleagues at the keynote in InfoAg many years back. He said, "Well, if you are chasing average, you're missing the target 100% of the time." And I said, "You exaggerated. It's 98% of the time." So, well, and when we showed this data, exactly like what you said, it's a mathematical mean. It doesn't exist anywhere. So to satisfy farmers' curiosity, we said, okay, how about we go plus and minus 1% of the mean? That may be more realistic. What do you think happens now? Yeah, 10, 12% depends on the field and so forth. In fact, to further illustrate our point, we went plus minus 5%, and now you're talking about 10 bushels on each side. Is still what happens is 40%. So you know if you're chasing average, it doesn't exist. It doesn't exist. When was the last time that you had normal weather? Right? It doesn't exist. So even with that plus minus 10% bushel on each side, even if you were to call that large window as average, 20% of the field, 1/5 of the field, you over-fertilized in this example, and 35% of the field, you did not apply enough. Okay, that's an oversimplistic version. There are soil fertility, soil scientists, including myself in the room, they will disagree. But this is just an example to give you a point. When you are chasing average, you're missing the target. And so this has been the key mantra for precision ag. How do we manage variability? Well, you can only manage what you can measure. So the key question is, how do you measure variability? And once you measure it, then how do you manage variability? And so that has been a lot of work in my lab, along with several other around the nation and the world. This is one of the fields that we did a lot of grid soil sampling. So we went out with a coarser grid. This work was done in 97, 98, 99. I'm kind of dating myself, so just bear with me. This led to development of a lot of science. So on one field, those 3 years, we went out and did a coarser sampling. And then in one part of the field, we said, well, let's do a finer grade sampling. So we went out and sampled very intensively. And the farmer was saying, you're taking all the topsoil away to your lab. You know, we did so much sampling there. And just like any precision practitioner, you first want to estimate the spatial range, or the distance at which there's correlation versus no correlation. It turns out that for this sampling, the spatial range happens to be 15 meters. Okay, and that will require 2,500 soil samples to accurately capture. This is nitrogen. A lot of our work is with nitrogen. To accurately capture distribution of nitrogen in the surface soil, that will require 2,500 soil samples. Now, how many of you students will sign up for that? Let alone farmers or practitioners. It's untenable. And the nugget effect is so bad that for all the sampling we did here, amounted to nothing. You cannot interpolate. Now, there are a lot of softwares out there. You click, 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 will create the surface that has no technical merit. Okay. And so there was a book that our good colleague and friend Margaret Oliver and Ruth Carey edited. I have a chapter in there. And in the very opening chapter, Margaret says, well, for you to do accurate prediction, you not only have to measure variability at the spatial range, you have to do that at half the spatial range. So that's an exponential function. If you pull out your calculator, it's a 55-hectare field, you do the math, now we're talking about 7 meter by 7 meter. How many soil samples now? 10,000. Exactly, it's an exponential function. It's 10,000 soil samples before you do that. So we learned it really quickly that, look, it's labor intensive, time consuming, and not economically affordable. We need an alternate. We need an alternate that can accurately quantify variability without those parameters. So, and yet throughout my journey in my precision ag world, we want something that's diagnostic. So grid soil sampling is diagnostic, okay, but it's destructive, okay, and time consuming, labor intensive, cost prohibitive, and must be deployed at spatially dependent scales if you want to have meaningful outcomes, okay? So it became very, very hard. And that's exactly what led to us writing the proposal in 1999 that was funded partly by NASA and USDA. There used to be an initiative called IFAS. So my lab was one of them that got that funding for $1 million, which used to be a lot at that time, still is today. And so 4 of my PhD students worked on developing 4 different techniques of management zones. So they worked on looking at so many different ways. How do we capture variability, employing remote sensing, bare soil imagery, topography, farmers' experience. In those days, we didn't have access to 10 years of yield map. And and this became a commercial product. There's a company called Centennial Ag that was the first one that embraced it. And then iterations of this was picked up everywhere in the union and north of the border. Canada uses it and so many other places as our work has taken. So we needed data collection at high spatial densities. That has been our question, and how do we address that? So fast forward, this is 2012. I had a quarter of a quarter section. Okay, so quarter section is 160 acres. So we have a quarter of a quarter section that was furrow irrigated. I got some money from my endowment, and I said, I'm going to put in a precision pivot systems. Okay, so this still exists, and this is one of our sites where we continue to do work. And so the system that we built here is a precision irrigation system, one of the very first ones at that time in the country that has drop nozzles 5 feet apart, and you can change the rate of application of water at every nozzle level. Okay, so mathematically speaking, you have 5,000 plus management pixels, right? And here's the drop nozzle that you can change the rate of application at every nozzle level, and you can actuate that at every 2 degrees of pivot movement. You do the quick math, and so that's 5,400 mathematical water management zones. And this is where I've said in my papers as well, that technology is ahead of science. This is the technology I'm working with. Where is my decision map? And we're still working on this today. Where is my decision map? Does it even make sense to be applying differential rates of water just because I have technology, right? Okay. And then there are so many unknowns. Does it even make sense to apply differential rate? I just said that. How do we figure out how much water to be applied in each zone or in each pixel? How many zones are ideal? Do these zones change? Do they change every season or every time you actuate your pivot or lateral? Okay, how often does that change? How much does it change and how often? And how do I measure if I have the tool to manage? My management pixel is 5 feet by 5 feet, roughly, right? It's a quadrilateral, it's not a square. And so how do I measure? So that quest, before it was only for nitrogen, then we started dabbling with water. Water and nitrogen go together. I've always worked in irrigated systems, okay? And so we said, how do we measure that? You'll go back to the drawing board, you go out, send your students out to measure with TDR soil moisture on the surface soil, calculate that. This is their spatial dependence. And based on that, this field, this is a 22-acre pivot, needed 84 sensing nodes. So I wrote a proposal to John Deere. John Deere used to be in water systems at that time. I said I need 100 sensing nodes in my system. They said, you guys are crazy. We said, well, we know it, but we still need to do it, okay? Because I need to be able to quantify. So this is wireless sensor node. John Deere gave us about 10 or 12 such systems. We later have partnership with Hartau, and they gave us some more systems. We couldn't do this work. And imagine 10-foot tall pole in these many locations in the field. Farmer is going to love you, right? This is not the way to go. And each sensor node is about $3,000 to $5,000 in 2012. Okay, we did this work on one half of the field. Okay, and bless his heart, Dong Wei, he was a visiting scholar, postdoc in my lab, and he was looking for a project. He got excited. I can do this. So he went out with access tubes to measure soil moisture every week, sometimes twice a week, to quantify how much was in the profile at 5 depth. And Louis led this work. We established spatial and temporal variability, and there was some key messaging. This was so good for the irrigation company that there has to be dynamic water management zone each time you actuate your pivot, okay? In fact, the zone could change because pivot may take 2.5, 3, or 5 days to go around the entire field, okay? So the challenge was, how do we measure soil moisture in situ, non-destructively, at spatial dependent scales? And why just water? Why not other parameters as well? And lo and behold, 5 years back, John Deere came out with this spray, CN spray, that you can actuate any nozzle. So now again, your management is like 2 feet by 2 feet. And how many sensors would it take to measure? And we're talking diagnostic measurement, not surrogate measure like remote sensing or sensor-based. And so this challenge has been something that we have been trying to address, okay? We want high spatial density, diagnostic, rapid, inexpensive. In fact, that became part of the chapter that I co-authored at the National Academy of Sciences Science Breakthroughs 2030 report that was presented to Congress in 2018. And we said, okay, could we try that with sensors? So I'm going to show you some of the work that Louis did while he was in my lab. We said, how about we go to the sensor route? Okay, look at inexpensive sensors. Can we do that, right? It's diagnostic, high spatial density, and so forth. So there was a company out of France reached out to us. This used to be a $40,000 sensor. They said, well, we'll present it to you for nitrogen purposes. At that time, they were only selling this to vineyards to measure the phenolic component of the grapes for high quality wines. We said, okay, let's give it a try. And Louis came up with the idea, how about we measure optical properties using fluorescence in soil? I said, well, does it even make sense? So he did some literature review, and lo and behold, there was literature to back it up. And that's exactly what he did. So it's a multiplex fluorescence sensor. There are 4 induction channels, ultraviolet and RGB, and there are 3 detection channels. So your output is 12 different parameters. And of course, you can create your own ratios to come up even more. It's actuated at 400 hertz. And so in every second of your work, it generates a lot of data points. You use it for 1 second, it's just boatloads of data. Okay, the longer you work with it, it's just you're collecting data, and more data. Okay, and so he went out to the field, came up with a randomized sampling design. This is Louis working with the prototype, newer version, a lot lighter, newer version. And it was in a bucket. He's very good at fixing things together, and he walked the entire field. That's what he did, okay? And so that's a closer shot of how he was doing that. And so he walked everywhere and was collecting for several seconds. What else we did, we took soil samples from there. So he took it out in the field, and then we dried it, created a uniform pattern, and then had our student help us out with that. We did this work for 3 years, over 9 sites. That's Tani. After drying it, she's working in the lab, ready to shine or fluoresce the soil and take measurements there in the laboratory. So these are our samples. Visually speaking, I can't see a whole lot of difference other than color. And this data sat with us for a long time because it was hard to figure out what can we do. We recently hired a postdoc who has machine learning and artificial intelligence competencies, and he was looking at the data. And so I'm going to draw an analogy here. And so how do we deploy machine learning? I've had a big extension appointment, so I tried to break it down here. So we said, okay, how do Google, or these cameras work, right? What do they do? They're training the cameras all the time. You're taking so many pictures. So I'm going to pick up one of the global celebrities. How about Bill Gates? Okay, so everybody can recognize Bill Gates. So here's Mr. Gates with the same, glasses and similar looking sweater, and you tell the computer, hey, that's Bill Gates. Okay, that's Bill Gates. That's Bill Gates. But here he changes his orientation, and the sweater changes. You tell the computer, hey, this is also Bill Gates, right? And he may lose the sweater. Okay. He may look different, right? So what we're trying to do, we're trying to train the computer. And that's one of the fallacies we have, that we need lots and lots of data to first train the computer. And that doesn't exist in agriculture right now. How many iterations do I have for the pivot for me to train the machine so that it can go into the predictability? So what happens? He loses the sweater, his orientation changes, and you're mixing it with different ages of Mr. Bill Gates. Can the computer still recognize it? It makes mistakes. Google makes lots of mistakes. You know that, right? And it gets more and more complex. He's getting younger. The pattern behind changes. He loses the sweater as well as the jacket. What happens now? Would it recognize? What happens if he gets very younger? Right? Can it still accurately identify? And then if you do enough learning, can it now predict how it's going to look next? And that's exactly what we're trying to chase, that if I train the pivot and the sensors enough so that the sensor can look the information ahead of the pivot, feed that information on the edge computer, and send the decision back to the pivot so I can apply the right amount of water at the right place at the right time, right? Our USDA goal by 2050 is to cut down our water footprint by 50%. I'm in Kansas sitting on Ogallala. Last year alone, it depleted 2 feet. The report came out last week. It depleted 2 feet. So it's not going to stay there forever. Last year was a very dry year. Okay, so how do we do that? And what happens here? Who is this? Thank you. So there is no substitute for human intelligence. This is Steve Jobs. It turns out Mr. Gates used to look like him too back then. And what happens if, look at the comparison. It requires a lot of training. Now, this is only the visual element, right? The difference is only visual element. That I'm trying to make it very easy here, okay? And it gets very complex. And what happens here? Those two are very different looking individuals. So will the machine perform what we're training it to do? And about soils are simple, right? It's mighty challenging trying to train the signals coming from soil, not just physical property, but also chemical property, to see, okay, what can we learn from those iterations? So here's the data set. He averaged it. This is Dipankar. He averaged the data. And so now you have that many predictions. So 12 channels plus some more modified indices. And then you are basically running mapping in multi-dimension, right? That's what you're trying to do, okay? And you start looking at what are significant relationship. We picked up 3 or 4 of those. Based on that, he parceled 70% of the data to train the model, okay? And then he used 30% of the data to test the model. So training, R is 0.91, R is 0.57. One of the things we realized that the fields where we were doing sampling had very low nitrogen parts per million. And so we did a better job with low, and the model really stinks as you get into higher parts per million, okay? So again, it's based on what we are training the model to perform, right? What can we do next? If one day we're successful, and there are many laboratories that are trying to resolve this challenge, okay? If we're successful, we can have an unknown soil sample, use some kind of technology, I'm not endorsing any, and then you do go through the optimum feature selection, have a trained model, then the regression, you have a soil estimate, and you go to the end recommendation. I want to caution you, it requires huge amount of data for the training purposes. Your results is only going to be as good as what you can train it. But you can collect data in high spatial density. It used to be 40 grand. I think it's now down to 19,000. Okay, so the more such, and there have been improvements in version. Diagnostic, no, this is also a surrogate measure. Rapid, person has to go out. You can mount it on a machine, but this unit right now fails miserably in motion. Okay, so person has to walk over there, actuate fluorescence, and then move on. Inexpensive, no. Data processing and analysis requires high amount of skilled labor. Okay, so this has been our quest. That how do we get spatial, high density, rapid, and inexpensive? And so this is again Louis and Raphael out in the field sampling. Our best technology that's affordable is out there, make a soil solution and do a nitrate test check. Okay, it's more qualitative than quantitative, or there's a LACWA meter that gives you, in parts per million. Okay, so that's what it is, right? Now, talking with engineers, they say, hey, we can measure this. And so you have a reference electrode and a working electrode, and you have got a power circuit and reader. If we can identify a working electrode that can measure nitrates in salt solution, you dip it and you test it out against different molar solutions, and the response to voltage is fairly good. And as you change the molarity of the nitrate, sodium nitrate, it gives you a stair step. So that's an aha moment. Can we translate that into a very inexpensive nitrate sensor that can measure nitrogen distribution in soils at high spatial densities? Diagnostic, rapid, inexpensive, destructive, involves labor, time consuming if you have to go out and do it yourself. And that's exactly what I was referring to, the Science Breakthroughs report that I was part of at National Academies. And if you read the chapter, it mentions that this ought to happen if we want to go to the next level of precision management. It says it out right there. And for us to become competitive in the proposal world, we added 3 more things when we wrote this proposal to ARPA-E. We said our sensor will be batteryless, it will be passive, and we'll build it on a biodegradable material. We didn't know what we were signing up for. We got the grant, and I was making this presentation at the Western Governors Forum, annual forum in Las Vegas, and I was making a point that I need sensors that I can literally distribute it out in the field that are inexpensive and so forth. And then I ran into an engineer saying, we can do this. You know what? We can actually print the sensors for you. And we are doing this in our lab. I said, really? And so I said, okay, so that became the holy grail. Then last 4 years, we have been working my lab with UC Boulder, material scientists, and UC Berkeley, computer engineering and computer scientists, to develop biodegradable printed sensors. And you literally print it on a screen print, okay? And so you have a reference electrode, you have insulating layer, of course. This is how, once you have the screen made, that's how you print it on a conductive ink. I gave this very detailed presentation at the last American Society of Agronomy meetings, and you can literally print it, and then once you have the electrodes that matches up, you can dip it into the solution to start measuring, okay? The first prototype is 8 of these sensors are in the greenhouse testing going on right now. We have been developing nitrate as well as soil moisture sensor that are being printed, okay? And so this is, version 0, right? And of course, we're using a circuit board because we're far away from degradable sensors. So if we are successful, our idea is that we'll have a degradable material, okay, that will print the circuit and the electrode directly on it. It can be done. Conceptually, it can be done. It proves okay. The sensor works fine for 2 or 3 days in lab conditions, okay? But it fails miserably. It has been lasting right now. We are beyond 2 weeks. It's working okay, okay? The nitrate is really finicky, okay? So it has some of those properties reliable. I will not go that far, okay? It drifts, inexpensive, batteryless, passive. Also, we're decoupling the biodegradable element. If we can just get a nitrate sensor that works, that inexpensive, you can print it, I think that will be a win. And accuracy and precision are again, there's so many hoops that we have to jump that we're not there yet. We went through a lot of material testing where we did accelerated degradation. We'll put in harsh environment, put it on the shaker for 24 hours that I don't know what the sensors will experience in the soil. What happens if the plow goes right through or the vortitil goes right through? What happens to the sensor? We did that. We also continuously are doing field studies in the greenhouse with different materials. When you use different soil types, sand versus peat versus clay, the performance and the drifting of the sensor happens big time. There are lots of hoops to be jumped, you can imagine. And then we keep taking destructive samples to see at different time frames that how the sensors or the sensor materials are behaving. They don't behave so well. Now, we do want these sensors to fail at some point of time, but our time target is 200 days. So you distribute these sensors out in the field. You don't have to go back and collect them, okay? And then they break down and they go. You can tell we won't get rich selling these sensors because our target price is like, a few pennies, okay? You can just print them, right? But the money is not in the sensor, the money is in the data. Because farmer won't invest. I could imagine practitioners go out and embed the field with sensor technology, and then you're collecting data in X and Y and Z depth and time T. So you're working with multi-dimensional data set. It'll require a lot of machine learning and AI algorithms for us to get to the decision map. We have been publishing all along in some good journals what we are learning. We did a lot of dummy sensor field testing with different, because it has to be encapsulated so that the sensor don't degrade before we want it. A lot of grunt work has been going on. Lots of successes, tremendous amount of failures. I can tell you right now, this is not easy. And how the same sensor behaves in different soil types. We're very cognizant of that. We're not close to where we could be. Moisture sensor, from our learning, we're a little bit closer than we are for the nitrate sensors. You start with the biodegradable material, you etch it with a stencil, then you fill it with the conductive ink. You etch the conductive ink again so that it can conduct whatever signal we're trying to do, and it becomes conductive, and that's where we add a couple of wires so that now we can communicate with that, and then you encapsulate that with a wax coating. If the video still works, it's a good one. This is one of my co-PIs.
This is the balsa wood substrate
Right.
that we print on.
Right.
So we put a stencil on top,
Right.
in the shape of the electrode pattern,
Right.
right? And then we use just a blade to coat through this stencil pattern.
And the ink is right
And
here.
we use an ink like this.
Yep.
Yeah, exactly. We use a zinc ink.
And when you do that,
And when we do that, we get a electrode pattern that prints on the balsa wood that looks like
Correct.
that, made of the zinc,
correct?
but it's not conductive. So we
Correct.
have to make it conductive. So we dip it
Yes.
into a solution of acetic acid,
Correct.
which etches the zinc oxide layer and
Correct.
makes it conductive. Then we attach wires
To be able
using
to communicate.
to be able to communicate with it, to interact with it. We use like an epoxy to do that. We
Yep.
connect the wires.
And you use this mold.
And then we use a mold, and in the mold, we then coat the wax. We have to be very careful. Like a lot of the trick in this is coating the wax and making sure there's no cracks.
Gotcha.
Right? The wax is like you can
Got
see it's
it.
a very good wax coating.
Correct.
And so that's trick, and that is basically a complete sensor,
If I
right?
go closer, I will see the communication wires
You can
right
see
there.
the wires, yeah. So
Right.
we can connect these obviously to electronics,
Okay.
and then ultimately in the future we'll just connect them to a RFID.
So the first prototype may look something like
like
this.
this, yeah. And
It's
so
missing the board right
it's
now.
missing the electronics board, which will go there. So there'll be an electronics board here, which will do Wi-Fi communication.
Okay,
These two wires will connect to that board,
Board.
and then this will go in the soil
Correct.
up to about there to make the
Right.
measurement.
Right.
And that'll be what our first measurement.
and we can program it such that it can record at any frequency we choose.
Yes,
Okay.
yeah, within reason, yeah.
Okay, excellent. Thank you.
Yeah.
So it doesn't have any battery. Okay, we use a radio frequency wave. The sensor is sleeping all the time. We wake it up for a millisecond. It does the work, soil solution around it, measures it, sends the signal, and we record it. And as many times as we actuate it, it provides the
So
number.
this
Sorry.
is the balsa wood substrate
Right.
that we print on.
Our vice president of research office did a cover story on the work that we're doing. I don't know how they took this picture, but it's a pretty good looking picture of this. This is just a starting point for sensor node setup that we have. We always measure it with commercial sensor to see how well the commercial sensor is performing against our sensor network. We always grow plant on it, just want to make sure. When you do these kind of things, commercial vendors reach out to you, say, hey, we have figured this out. By the way, would you like to do that? So we created a test bed. There's a company out of Finland that reached out to us. Apparently, they have been following our work for the last 20 years. And they said, well, we will give you those sensors. These are battery-powered sensors. They're very small, but the battery will last 20 years because the sensor is sleeping all the time. It's non-degradable and stuff. So we did create a test bed at the North Farm. This is and we had to go through a bunch of hoops in order for them to be pinged and data to be read. So here's the base station. solar powered Wi-Fi module. In these rows are where we had 24 sensors in a field size of like this room. That was our test bed that we did last year. And so we actuated from our lab and you can program it for frequency. And then my postdoc wrote a app that you can immediately create a surface map or a heat map, that as he calls it. So this is a 2-dimensional heat map, and we did this at 2 depths. Okay, so as many times as you actuate data in X, Y, and Z, you can. Oops. So you can have this data. This is only for the surface for multiple times. What happens with depth? I don't know what weight should I give to 6 inches depth versus 24 inches depth versus 36 inches depth? We don't know right now. So there's a lot of unknowns. This work that we have been doing for the last 10, 15 years. We go out and measure electrical conductivity. So what my lab has been doing is, till we don't have the sensors, we don't need to wait to work with spatio-temporal data set. So in any given year, we collect 30-some data layers, and I'm just stacking it up right here to create that big data set and train it through machine learning, employ some of the AI algorithms. These are self-explanatory, that what kind of data layers that you can collect, all the way down to the yield map, and then help translate into a decision. I don't even know what the relevance is, or weight matrix. Could you imagine the weight matrix? That which data layer has more weight in the decision? And each parameter, I mean, we're doing farming for centuries, right? But we don't have this quantitative assessment of how it impacts our decision making. And I've given some keynotes on farming with data, but there are a lot of questions we don't know. There's a lot of graduate students here. This is PhDs written right here. We don't know what data not to collect because it doesn't matter. So we're going out and collecting whatever we can lay our hands on, okay? Or whatever the graduate student agrees to collect, right? What kind of biometrics or statistical computing would be needed to understand relationship within and across these spatio-temporal data set? We don't know that. What's the weight assign and the role, right? And how do we account for seasonal anomalies? It's going to happen every year. Okay, how do we ensure this is reproducible and reliable? And honestly, and this is the proposal we wrote to USDA. The title of the proposal is Artificial Intelligence for Sustainability of Agriculture. My role is water and nutrients, and then there are other groups that are looking at salinity and pest management and diseases. It's a SAS grant that we have in motion right now. And so this list is very long, what we don't know. Okay, so we have graduate students who are working on it. I can envision that someday we'll get to a point that we'll have in situ, non-destructive, rapid, reliable, inexpensive sensor network that will be collecting data layers, that will be feeding it along with other data sets, okay? And then we'll employ machine learning and AI. We'll keep the complexity to ourselves, okay? And it'll be automated somehow, but the decision power will still be in the hand of the farmer. Hey, I don't like this decision. I want to put 20 pounds more. No matter what you're telling me, I'm gonna put 20 pounds more. And that's, I think, could be part of the solution. I'm not saying this is the only solution. That by 2050, we can reduce our inputs, nitrogen and water, by 50%. I'll welcome any questions. Thank you. Yes, sir.
So you mentioned that this approach requires machine learning and artificial intelligence, but I was noticing in your illustrations, especially on the first slide, there's no human beings in these systems. So I wonder if you could talk about what the role of human intelligence and human farmers is in this approach, in this paradigm.
So the question for those who are online, the question is that you're talking about a lot of ML and AI. I did not see much human intelligence and human intervention. You cannot eliminate human. Because I sure hope that we are not requiring all those data layers to be captured. At some point in time, we'll figure it out that I don't need to go out and measure soil moisture distribution at 30-minute frequency just because weather data is recorded, or 30 seconds. Weather data is recorded that way that I have to record soil moisture at that frequency. I don't know that. We would like to, and this is where the element of human intelligence come into play, okay? And as I said in the previous slide, that we're not eliminating farmers. So farmer will have the final decision-making process, okay? And that most likely will be happening on their smartphone or iPad or whatever interface that we'll be working with. We don't want to overwhelm farmer or, for that reason, practitioner in the decision-making process. We want to keep that simple, keep the complexity to this group right here. But I mean, think about many of the technologies that have been successful and have been picked up were intentionally kept simple, built on a very robust, complex systems. So we are never eliminating human intelligence. Yeah, not in our lifetimes, at least. I know there's an AI chat GPT and so many other things out there. Yeah, good question though.
So my question is, how are you going to integrate this? I mean, you already have sensors out there. They're called plants. So at what point are you going to be integrating plant information into, they're doing already the integration for you. What's the link there?
So you're exactly right. Question is, how are you integrating plants? So our group is taking surrogate measures from crop and plant responses. There are other groups like mine that are working on in-planta sensors, where they're, you're using stickers to stick the sensors to the leaves, zapping in electrodes to measure the sap content continuously. There are several AI institutes that have been funded through NSF $20 million grant that are developing those in-planta sensor for do exactly what we are doing here. Our focus has always been on nitrogen and water.
Later, we're going to have to move away from actually putting things in plants and basically using, I don't want to say remote sensing, but in a sense, sort of because you can't just keep putting sensors out there. You need to be able to have mobile. Maybe
that'll happen. I don't know. Maybe it's a combination of things that'll happen. I do not know. Right now, we're just trying. And NASA in year 2000, they had an in-planta sensor, by the way. I was looking at the NASA Innovation news report. They tested that, and they were measuring the turgor pressure of the plant. And they programmed it to a cell phone that every time the turgor pressure was dropping, you get a text message, hey, water me, right? So, I mean, there are some simpler technologies that are available. It's just right now it's picking it up. And it will involve a lot of frugal innovation. Yeah. Because if you're trying to do it at high spatial densities, even large farmers can't afford it.
I'd like to see where the instrumentation gets tied into plant performance. So you've got all this information about soils or climate and things like that, but what is that implication for plant performance?
And I don't want you to carry this impression there is equal or larger body of work is being done with plant as sensors. Yeah. Yep, I did not cover that today, so.
All right, so for
Pippin,
the rest of time,
Pippin has a question.
do you want to ask a question? Okay, you go.
It's for the online.
Yeah, for the online people. Sorry.
Excellent presentation, Dr. Khosla. I would like to see what's your envision on big data management and regulation policies. There's so much data has been, going on, creating. How will it look like, the access to this big data to the stakeholders, practitioners, public, general public?
Right. The question has to do with the big data and the security and the ownership, and how does that look like? That conversation is happening nationwide. Right now, we don't have a resolution on that or consensus on that at right now. So farmer still owns the data because there are so many private companies that are collecting huge amount of data. The raw data is still owned by the data, and the fine print says that the derivative, my understanding is that the derivative could be used for other purposes, but not the direct data set. Just this week, Monday, we visited a farmer who manages 43,000 acres in Colby. And he has been collecting data for last 20 years. And he was one of the rare farmers. He was very open to giving the data set if we can translate that into meaningful decisions. I've not found a lot of farmers like that. And it goes into a cloud. You know, he was a John Deere customer, and of course the derivatives are being derived, so that continuous improvement, whether it's machine performance or labor working in the field or not, or pivot is clogged, or whatever that might be. But we don't have a solution on the ownership, if that's what you're getting at right now. Yeah.
All righty. Thank you very much, Raj. So another round of applause.
Thank you.
This has been a production of Cornell University, on the web at cornell.edu.